Hey guys, so this is today's lecture on nuclear chemistry. We started it yesterday with the uranium-238 decay series, and we are going to continue talking about the history and some of the particles. All right, so an interesting story was how radiation was actually discovered. So back in the 1800s, the late 1800s, they were studying fluorescence, which everyone's familiar with fluorescence because you put a black light and your t-shirts glow, and sometimes we have posters that glow. We have glow-in-the-dark t-shirts and items that you can put in the sun or under a light, and then they glow. That's fluorescence. And somebody was studying fluorescence, and he accidentally discovered X-rays. So the kind that you get in the doctor's office. So Antoine Becquerel was also studying fluorescence and phosphorescence. And once he heard about the X-rays, he started trying to link X-rays to what he was studying, which was phosphorescence. And so he was exposing plates, photographic plates, to light and trying to develop them. All right, so what he did is he took these uranium salts, which he just happened to have in his lab, and he put a black paper on top of his photographic plate, and he was going to expose it to the sun, but the day that he went to do it, there wasn't any sun. So he put it in his drawer and kind of forgot about it for a day or so, and when he went back to actually use those photographic plates, he thought that maybe there'd be a little bit of fluorescence there because, you know, when you're not using the light or the sunlight to expose something that glows, it doesn't really glow after a while. And so he was shocked when he opened the drawer, and what he found was that the entire plate was exposed. And all it has were these uranium salts. And so if you take a look here on the bottom of the slide, you can see a cross that was actually sitting on top of his photographic plate. And so he was amazed by that and knew that there had to be something else going on besides just X-rays and fluorescence and phosphorescence. And so he actually discovered radiation. He just didn't know it at the time. So luckily in his lab, there was a woman named Marie Curie. You may have heard of her. She was his student, and she was studying for her PhD in chemistry. And so after he discovered the exposure of his photographic plates, he decided to task her with studying it even further. And so she used that for her doctoral dissertation. She was married to Pierre Curie, and he was a physicist of the time. He had invented with his brother-in-law this thing called an electrometer, and she used it to study the activity of the uranium. So what Becquerel wanted her to do was take this thing called pitchblende, which is just a rock, a mineral, and he wanted her to study it and see if there was radioactivity in it. And when she measured it, she found out that it actually had about 4 times as much activity as the uranium salts did. And so Pierre and Marie, so he actually stopped his research because this was becoming so exciting, and started trying to get something out of the pitchblende because they decided there has to be something besides the uranium to make it more active than the uranium salts. They actually took a kilogram of pitchblende, so you can imagine just a ton of this rock, and they extracted milligrams of 2 new elements, which she is given the discovery of, which was polonium. She named it after her country that she used to live in, which was Poland, and radium, which is after radioactivity. She's actually thought to have coined the term radioactivity in 1898. The problem at the time, though, is that because she was a woman, she wasn't actually allowed to talk about her discoveries. So at the time, what you would do is you would go and you would speak to other scientists, or you'd write papers, and that's how you got your discoveries out. And at this time, everything was happening very fast. And so they needed to get this information out as soon as they discovered it, so they got credit for it. And she wasn't allowed to actually go and speak to other people because she was a woman. So Becquerel had to go, or Pierre Curie had to go and do the talking for her. Luckily, all 3 of them actually ended up winning the Nobel Prize in 1903. She, again, almost didn't win the prize because she was a woman. And at the time, they never had any women scientists win it. So there was a lot of discussion at that, but they did give that to her. She's actually one of the few people who's actually won 2 different prizes. 1903 was in physics, the Nobel Prize in Physics for the discovery of polonium and radium. And then she won one in 1911 in chemistry. So she's won 2 different Nobel Prizes. Unfortunately, she ended up dying due to her exposure to all this radiation. They say now that her notebooks and even her cookbook from her house have to be lead shielded because there's so much radiation that they're dangerous to even look at in a historical reference. All right, so we keep talking about radiation. I told you radiation gets a bad rap. So if we look at the electromagnetic spectrum, this is all of the radiation or things we call radiation in the world, kind of broken down based on how big of a wave they produce. So if you produce a large wave, like things like the earth, the subways, radios, TVs, cell phones, it doesn't have a lot of energy. If you go to the other side of the spectrum up here, you can see that there is a lot of energy because the wavelengths are much closer together. And so when you have more energy, then they can do more damage. This is what's called the ionizing radiation. All right, our ionizing radiation are things like natural sources. So you can get it from the ground and the earth in many different ways. You can get it when you go to be treated for cancers or they test you, they're testing your organs using nuclear medicine. You can get it from x-rays. We've all had a lead shield put over our chest or our arms or something to get an x-ray. And then also fission and fusion. And coming in from the sun, there's ionizing radiation that can come in. Most of the radiation that we're exposed to is considered non-ionizing. Non-ionizing, all it does is make the molecules and the atoms vibrate and heat up. So like our microwaves, that's what happens with our microwave. We heat up the water molecules that are in there, and then it cooks the food and reheats the food for us, or the radio or the cell phones. Your toasters, electrical wires, other things have non-ionizing radiation. Now, if you look here in the visible spectrum, which is the sunlight, sunlight's kind of in the middle here. All right, we know that it has some ultraviolet rays. And ultraviolet rays, you can see, start to have shorter wavelengths. And because of that, they have more energy and can do damage. So we know that you can get damage from sunburns, but then we know also that this higher energy in ionizing radiation actually goes in and interrupts some of the DNA in your cells, and that's what ends up making it harmful to us. All right, so we talk a lot in chemistry about chemical reactions, but now we're focusing on nuclear reactions. And it's very similar. Chemical reactions happen with the electrons. Nuclear reactions happen in the nucleus. So radioactivity, the term, is energy and or particles that are ejected from an unstable nucleus until a stable arrangement is found. We saw that yesterday with our uranium-238 activity. We went from an unstable nucleus all the way down until we got to a stable nucleus. All right, and so we're talking about the nucleus. And in the nucleus are 2 particles called the protons and the neutrons, and we call them nucleons. If you ever thought about it, did you ever wonder why these nucleons all stay together? Why are they bound in this little tiny nucleus? So they're all positive particles. So positive particles should move away from each other, right? So we know with magnets, if you put 2 positives together, they repel each other. So why aren't these, excuse me, why aren't these particles moving away from each other? And what we found is that there's a strong force or a binding energy that is in the nucleus. And this holds the nucleus together. And again, this strong force over short distances is so strong. It's actually stronger than chemical bonds and things, but it only works over tiny short distances. Chemical changes happen at the level of the electrons, and we're going to talk about that in our next unit, but right now we're focusing on the nucleus. All right, so yesterday we talked about different types of radiation. So we have alpha, beta, and gamma, and we know that we can get our unstable nuclei to become more stable when they emit these particles. And what it does is it changes the arrangement of the nucleus. So protons and neutrons change places and try to become more stable. We also talked about gamma being just pure energy. We also have things like a neutron can be ejected. We can have positron, which is a positive electron. We can have a proton that is ejected, and you can have other isotopes. So we saw those again in our activity yesterday, that there's different other unstable isotopes that come out of a reaction that then also have to decay to something more stable. So we talked about balancing nuclear equations yesterday. We have our reactants on the left, we have our products on the right, and we have to balance the mass numbers. We have to balance the atomic numbers on the bottom. And you do that by adding in other isotopes and different particles. So let's talk more about our alpha radiation. Our alpha radiation is, again, a helium nucleus. All right, so it has 2 protons, 2 neutrons, and just the nucleus of a helium. It is considered matter because it has mass. It's the least powerful form of radiation, but it actually can be the most ionizing and damaging to living cells if inhaled or ingested. So they have used this in history. Just recently, we've had some Russian spies who were poisoned, and it turns out they were poisoned by alpha radiation that was in foods. It's also used in your smoke alarms, and most smoke alarms have 2 different pieces of foil, and we have radiation going back and forth between the 2 plates, and the smoke will go in and interrupt that movement, and that sounds an alarm. So that is alpha radiation. Our beta radiation is when a beta particle is ejected. And as the beta particle is ejected, a neutron is actually changed to a proton. And so you can see that's why the atomic number goes up. It's also considered matter. It is a high energy electron, and it moves very fast. And an example of this is not something maybe that you're totally familiar with. Excuse me again, but in nuclear power plants, they have to take the spent rods and put them in water to cool down and to go through their decay series. And we'll talk more about that in future lectures. But there's a blue glow about that pool. And that blue glow actually comes from beta emission of those spent rods that are going through their own decay cycles. So that's where that comes from. You can also use beta decay as a way to adjust the thickness of aluminum foil, which is an industrial use. Our gamma radiation, again, I have another picture of the electromagnetic spectrum, is high frequency, short wavelength. So remember, we talked about up here on this side of the electromagnetic spectrum. It has many uses. Again, it is just energy. It is not matter. It has great uses, like cesium-137 is used in cancer treatment. Cobalt-60 sterilizes medical equipment and foods. It can be used in medical imaging. It can also be found in nature. All right, so potassium-40 is found in the soil and water, in meats and foods that are high in potassium, such as bananas. So gamma radiation can be found naturally. But for the most part, we need to protect ourselves because there's so much energy in these waves that, again, it can go down and interrupt our DNA, which is problematic with gamma radiation. We have positron emission, which is a positive electron, which I know sounds kind of crazy, but it turns out that all matter has antimatter. So an electron has a positron. A neutron has an anti-neutron. So there is an anti of everything in the world. And so this positron is used in positron image tomography, which is a PET scan. So you may have heard people talk about PET scans, and it's when they need to look at the soft tissues in your body. So they put in this fluorodeoxyglucose, which is just sugar that has an an indicator on it, okay? So it will light up when it gets in your body. It turns out that tumors will uptake glucose much faster than normal tissues, and that's because they are growing and dividing so quickly, they need more energy. And so this fluorodeoxyglucose will go where the tumor is, and then it will show up on our imaging. So it turns out that this positron actually collides with an electron, and it has a process called annihilation. So when matter and antimatter come together, they annihilate each other. And so when this happens, it emits a gamma ray. So it's actually almost a way for us to produce gamma rays that then can be detected by the imager. We also, again, have electron capture, where we will take electrons from some of the outer shells and bring them into the nucleus. It produces a neutrino, which again is just energy. And one of the ways that we use this is in GC, which is gas chromatography. You can use it to detect drugs. So when they are trying to detect drugs for crimes or in some sort of forensic science application. All right, we talked yesterday a little bit about penetration. It was on the uranium-238 and how the radiation can penetrate certain things. So an alpha radiation, or an alpha particle, as you can see, can't even go through paper. It just doesn't have enough energy to go through paper. Beta can go through paper and then can be stopped by things like wood, thin pieces of wood or aluminum. And X-ray gets stopped by lead. We're all familiar with that because we've put on the lead jackets or the lead shields at the doctors or the dentist. Gamma rays can also be stopped by some leads. It depends, again, on what the lead is and how thick it is. And then a neutron can go all the way through to water or concrete. All right, so the penetrating ability of different types of radiation is shown. And so that's important in how you protect yourself from different types of radiation when you're working with them, or just the exposure to outside sources that we have in the world. All right, the band of stability. The band of stability is one thing you're going to be working with today. And the band of stability is a graph that shows the number of neutrons on the x-axis. It shows the number of protons on the y-axis. These black dots all through the middle are considered to be stable isotopes. And you are stable when your neutron to proton ratio is very close to 1. So if we have something like neon, which is neon 10, so if we have 10 protons, that would be neon. And we go up here, neon 20. So 20 is its mass, 10 is its atomic number. It has 10 neutrons. So 10 neutrons and 10 protons gives us a mass or a neutron to proton ratio of 1. And so this neutron to proton ratio here makes it a stable isotope. So not everything is stable. And you can see how this graph just stops dead right up here around 80. And it turns out that at nuclei that have an atomic number of 84 or larger are just not stable ever. There is no isotope that is stable. So everything 84 and above is unstable and has to decay to get to a more stable place. So this allows you to kind of predict what kind of stability you can have. If you're above the band of stability, you're going to have a beta particle that is emitted, because again, remember that changes a neutron to a proton and helps force you back towards this black line, which is the 1-to-1 ratio. If you are below the band of stability with your neutron to proton ratio, usually you have an alpha emission here that tries to help you get closer again to 1. All right. And so you're going to be graphing a bunch of different nuclei today that show the different proton or the neutron to proton ratios, and you're going to create your own band of stability.